sure I don't get Thomas in the video. Let's see. Hey there, Luke. Ooh, what am I doing?
Hello.
That was strange. Oh, I know what happened. Alright. Need to rotate until I get to the pith ball. There's the pith ball. I'm going to go a little bit further. So, Luke, can you see this pith ball here?
Yes, I can.
Right here? David, can you see the pith ball? Thumbs
Yeah,
up.
I can see it.
Can you hear me?
No, yeah, I can see and hear you.
Uh-oh. Can't hear you, David. See what's going on? Ah! Can you speak again?
Hello? Hello?
Ah, there we go. I had my computer muted. Alright, so what I'm going to do is remove the ground from here, and I'm going to put the Van de Graaff generator next to the pith ball. A pith ball, by the way, such a funny word. I feel like I'm lisping and saying piss ball, but originally it was made out of some special plant fiber called pith. And it was a particular kind of plant. It was a sola or soli plant, and people used to apparently make hats out of it. That's where pith helmet came from, which is also funny if you think I'm lisping. But now pith balls are usually just made out of styrofoam or something, which is what this is, but it's painted with a metallic covering. So the outside is a conductor. And the question is, when I plug this in, and I'm going to keep this ground far away, the dome of the Van de Graaff generator is going to be close to the pith ball, what's going to happen? And then the question is going to be why. Does anybody want to make any guesses about what's going to happen when I put these two things close together? But turn this on. Will the pith ball... There are really a couple of options for what the pith ball can do. No, I can think of three. It's going to sit there and do nothing. It's going to get pulled toward the Van de Graaff generator, or it's going to get pushed away from the Van de Graaff generator. Any guesses which one it'll do?
Pushed away.
What's that?
I'm guessing pushed away.
Pushed away. Why?
It's going to get hit with a force from the...
I'm just listening.
As the electricity flows from there, because it doesn't have a ground, it'll go into the ball, which would make it go that way.
Okay. So the electricity is going from here to there, and it'll make it go that way. So let me just plug it in. We'll see. I don't know if I have it close enough. Oop. And there, I've kind of, let me put it a little closer. Huh. It's not really behaving like it normally does. That's so funny. This thing keeps turning on and off when I use this outlet. So in the other class, and maybe the humidity is changing in here. In the other class, this was really pushing it away. And can you kind of see it's going away? It's going away a little bit. And then when I discharge the Van de Graaff generator, so this is a ground wire, so any excess charge that's in that dome right now can just go right back into the ground. If I stop grounding it, then the pith ball does get pushed away. That's hilarious. Let me just unplug it for a moment. So the pith ball is going to stay pushed away until I do this. So what do we know about the charges of the dome and the ball when they turn it on? What? If they were opposite, what would they do? Would they attract or repel? They're the same, yeah. So when I do this, what's happening is this is charging up, and the dome there are a bunch of charges that are collecting on it, but some of them are leaking off it. That's why if you're around here, you can feel this. And so there are ions that are kind of spraying out. And anyway, the ball is getting negatively charged. And then when I ground the Van de Graaff generator and get rid of its charge, they're not repelled anymore. And now they are repelled. So it's working pretty well now. It's working better than earlier. So now what do you think will happen if I touch the ball with this ground wire?
It'll go back to.
It'll what? Let's see. Yes. So it's repelled, but as soon as I touch it with this, it's working really well now. It'll be attracted to this too. And as soon as it touches this, then it jumps back to that. Oh, we've really got it going now. Look at that. Put this over there. I can feel my pants tingling. All right, I'm going to turn it off while we talk about it. So, does anybody want to explain why, first of all, when I ground it, why is it then attracted to the dome?
Because that's an opposite charge.
Well, once I ground this, what's the charge of the pith ball?
I don't know.
What?
It won't have to.
It's neutral. And let's just say this is negative. I still don't know if this is a negative Van de Graaff generator or a positive one. But when this is neutral and this is negative, they still have quite different attractive charges. So for a moment there, it could be that this is inducing the opposite charge on that, just like when you bring the balloon really close to a wall and you rub on a balloon and it pushes the negative charges away and makes the near side have a similar charge. So that's probably what's happening. As soon as I touch this, now this is repelling. Well, that's weird. Oh no, it wasn't repelling. It was just being attracted to that. So, one thing I can't totally figure out is whether this is acting. I guess I just grounded the thing. Whether this is acting like an insulator or a conductor. At any rate, as soon as it touches the sphere, it gains a bunch of electrons, or it gains the same charge that the sphere has, and then they repel one another. And then when I ground it, I get rid of all those excess electrons, which allows it to be attracted to the sphere again. But then when it hits it, it picks them up and it gets pushed away. So it's kind of like a person, if you would touch this and then let go and touch it and let go and keep grounding yourself, every time you touch it, your hair would start standing up again. But this is so light that it's more like the pie pans I put on top of here. It just gets thrown away if it has the same charge as the Van de Graaff generator. Oops, I'm always afraid I'll unplug the wrong thing. I better turn the air purifier back on. So that's that. I'm going to try to avoid the mistake I made last class. So the first thing I want to do is talk about tonight's homework, because I forgot to really explain the homework to the other class. We finished really early and it just felt like, I wonder why there's so much time. And I realized right after the people in the meeting had left. So let me show you the two things to do tonight. One is some practice, 18.5 practice, drawing some electric field lines. That's right here. It's pretty straightforward. And the other is to do the FET electric field hockey. The confusing thing about this is it's not in the packet. There's nothing about electric field hockey in the packet. I forgot to put it there. So these are the questions. You can get to these through Google Classroom. And I don't care how you record your answers to the questions. You could type it, you could write it, you could just think about it and just mark it done. It really doesn't matter to me, but these are things I want to discuss. Number 1 through 4. Number 5 totally optional. It says try level 2 until you score a goal. How many tries did it take? I was going to do this last class, but then I realized I was on level 3. I got to 67 tries, and I still wasn't even close. So level 2 might have been easier if I'd tried that. So do those. I definitely want to discuss these tomorrow because there's a question or two on the test that most people miss, and it's because they don't really understand some of the concepts that are covered in this. And this link right here will take you to electric field hockey. You can use the browser compatible version if you have a Chromebook. If you have a computer that'll work with Java though, use the Java version. I think it's better. I think that you have to download it and then open it up. I think that it responds more quickly and you get better resolution. I think it just looks a lot better with this. Except it looks like it's, oh, you know what? It's probably slow to open up because I'm streaming right now. It'll have you do a few things. One, it'll have you turn on the field. Definitely this is not working very well because I'm streaming. But anyway, field line should appear, and then there's trace down here also. I'm not even going to try to play this right now. All right. First, order of business at this point is to go over the homework from last night. Let me get back to here and go to my solutions. And I think the hardest thing about these questions was probably the directions on number 1 and number 2. And by directions, I just mean number 1 is asking what's the magnitude and direction of the electric field, and then number 2 is asking what's the magnitude and direction of the force. So I didn't have any questions in the other class about 3, 4, or 5. Doesn't mean you can't ask about those. So does anybody want me to explain how to figure out that number 1 is downward and 2 is eastward? 2? Sure. And you know, I might as well do both of them just because they're flip sides of the same concept. Oh, that's not good. Sure. Let's see. Wanted to be able to see questions at the same time I could see what I was writing, but I don't know if this is going to work very well. Okay, so number 2 first. This is a pain. So it's asking for the magnitude and direction of the force exerted on a 3.5 microcoulomb charge by a 250 Newton per coulomb electric field pointing due east. So here's my charge. I'll just call it Q. And this charge is equal to 3.5 times 10 to the negative 6. Micro is negative 6 coulombs. And it's positive, doesn't have a negative there, so it's positive charge. And the electric field is pointing to the east, so I'm just going to use some arrows to represent the electric field. And the key is that the electric field points in the direction that a positive charge would be pushed. So if I took a tiny little positive charge that's so small that it didn't actually affect the electric field at all, and I just looked at which way it was pushed, that would define the direction of the electric field. So the fact that the electric field is rightward, that tells me this positive charge would be pushed to the right. So the answer to this question is, since this is positive and the field is to the right, the force that's acting on this is going to be to the right, or east, since, you know, I guess this problem takes place on a map like this. So the field is eastward. A positive charge, which is what this is going to get pushed in the direction of the field. Now, if this had been a negative charge, if this were negative 3.5 times 10 to the negative 6 coulombs, then a negative charge would be pushed the opposite way. It would be pushed to the west. So that's number 2. I actually think number 1 is a little harder because you have to do that sort of thinking in reverse. So here you're provided the direction of the field and you're given the sign of the force, and all you have to do is say if it's positive, it's the same way as the field. If it's negative, it's opposite. But in number one, you're given the direction of the force, and you have to figure out, and the sign of the charge, and then you have to figure out the direction of the field. So I feel like that's a little bit harder. So number one, it says there's an upward force on this charge. So here's the charge, and the charge is negative 1.75 times 10 to the negative 6 coulombs. And the force that's being exerted is this way. So you have to think about this. This is a negative charge and it's being pushed upward. And what that means is that the field is going downward. Because negative charges always get pushed in a direction opposite to the field. If this were a positive charge, then the field would be going up the same way as the force. But since it's a negative charge, the field's going down. I think you'll see as we go through the electrical stuff, there's this big emphasis on positive charges. And most of it relates to Benjamin Franklin, who didn't know in the beginning what kind of charges flowed through wires. He thought it was positive charges. So a lot of the things we're going to do are just based arbitrarily on positive charges. I mean, they could have made electric field. Oh, projector went out. People at home, the projector went out. That was what that is. And if I can't get it going, I'm just going to turn this around and point at the board, and that'll just be fine. But maybe it'll start up again. Maybe. I did this once earlier. Oh, it did start up. All right. Does anybody have any questions about any of these other ones? 3 through 5? All right. So next thing we're going to do, I like to do this. I like drawing electric field lines. And I apologize in advance if I call them magnetic field lines. I've lost my GoPro. That's odd. Wonder if that's related to losing the screen in some way. Sorry. There we go. But now I've got the wide angle lens. So page 11, and if you like to draw, this is kind of nice. If you're good at simulating forces in your head, this is even more fun. If you're not, you can still do it. So drawings using lines to represent electric fields around charged objects are very useful in visualizing field strength and direction. Since the electric field has both blank and blank, it's a vector. So vectors, the definition of a vector is something that has magnitude and direction. So the electric field lines we're going to be drawing are a map showing the magnitude and the direction of a force that would be experienced by a positive charge if it were on this map. And it's not actually a force, it's a ratio of forces. So it's telling us if you had a 1 coulomb charge, then it would experience this force at this place. Like all vectors, the electric field can be represented by an arrow that has a length proportional to its magnitude. Did anybody notice the camera lagging a few minutes ago?
Yeah, when we were like standing over there.
It was lagging then? Okay. Definitely lagging now. So earlier in the year when we were doing river problems, for example, we would have a river and we would say that the boat is heading this way and the river current is going like that. Let me make it a fast river current. And then we could add the vector for the river current to the vector for the boat, and we would get the actual path of the boat would be like this. That'd be the resultant. So this was an example of, you draw a vector showing direction, and if you want to make it a stronger vector, you make it longer. But we're not going to be doing that with electric field lines. So electric field lines are often represented by lines whose magnitude is represented by proximity. So it's a little bit like a contour map. If you've seen a map where this is a mountaintop and you'll have a steep side of the mountain and then a not so steep side of the mountain, and the contour intervals look like this. Have you seen, you know what I'm talking about? So these are all equal elevations, and right over here the elevation's changing really rapidly. That's a little bit like what we're going to be doing, where you have close proximity of lines, then there's intensity in the electric field. These are the rules. I'm just going to write them down, and then as we draw these things, you'll see how the rules apply. So field lines, actually, this one I think you can figure out. Did a hissing sound just begin and just stop? Okay. No. So the field is all about the direction that a positive charge moves. So if I have, let's say, a positive charge here and a negative charge there, and I place a little tiny positive charge right here, which way is it going to go? Is it going to go toward the positive or toward the negative?
Negative.
Yeah, so it's going to go like that. So this would be an example of a field line that I just drew here. So field lines begin on positive charges and they terminate on negative charges. And that's because they represent the force that would be experienced by a positive charge. So positive charges get pushed toward negative charges, they get pushed away from positives. So all these lines we draw start on positives and they're arrows that go to negatives. The number of field lines leaving a positive charge or entering a negative charge is proportional to the magnitude. If you have a stronger charge, then you're going to have more field lines leaving it or entering it. The strength of the field is proportional to the closeness or proximity. I'm going to say proximity this time. Sometimes I write closeness here. Closeness is just not a great word. The direction of the electric field is blank to any field line at any point in space. So the best word here is tangent, but people get kind of confused on what that means. So I'll say parallel because everybody knows what that means. But parallel to a curved thing, it doesn't really make a whole lot of sense, except over very short, like infinitely short distances. So this last part, field lines can never cross. And what this is getting at is if you put a little positive charge somewhere in an electric field, and you ask, which way is it going to be pushed? It can't be pushed this way and also that way. It's just going to go one way. It's only going to accelerate in one direction. You can't accelerate left and right at the same time. So the field is unique. That's the word that's used for this at any point. So if the field line's crossed, that wouldn't be the same. The field line represents the direction of the field, so if they cross, the field would have two directions to that location, and that's impossible. So now, for some drawings. In these first couple of drawings, these two charges I'm not going to show interacting, but I do want to they're part of the same drawing, but they're not interacting with one another. And I'll explain what I mean later on. So this is going to be a charge of positive E. And we can decide arbitrarily how many field lines we want to have coming out of that. It could be any number we want. It just shouldn't be a ridiculous number because you get tired of drawing them. And it shouldn't just be one because it's an absurd looking drawing. So I chose with the other class and last year to do 4. And so these field lines come out of this, and they come out because this is a positive charge, and because if you put another positive charge anywhere around it, it would be pushed away. It would be pushed out radially from this. So that's the positive E charge. Now I'm going to do the same thing over here, except this is twice as positive. So what's going to be different? What's that? Double the lines, yeah. So I'm going to draw just what I drew before, but then I'm going to put another vector in between each of these, or another line. And if I were really drawing a nice map of the electric field, I would continue these. I could put multiple arrowheads on them wherever I want, just to show the direction. But I continue these out to fill up the entire area. So this is what is meant here by the number of field lines leaving a positive charge or entering a negative is proportional to the magnitude. This has got 8, this has got 4, this is twice the charge that is. And then also the proximity part, if you look at how close these are and how close these are twice as close, these are half as close. That's kind of a weird way to say it. And also as you move away from here to here to here to here, the distance between these lines grows, and that means if I put a little positive test charge out here, it would experience a smaller and smaller force. The electric field gets weaker as we get farther away from this, and you can see that by the way the lines spread out. Alright, so that's a couple of positive charges, and now same thing except I'm going to do it with negative charges, and I'm going to make this a little bit different just because I can. So how should this drawing be different from that positive E? So one thing I need to make sure I do differently.
Arrows go away from the negative charge.
Garrett, is that correct?
No, it goes into it.
It goes into. So in here the arrows go away from the positive charge because these maps, this is the thing that just is really hard to get solidified in your head. All these maps show the direction that a force would be exerted on a positive charge. So positives are going to push positive charges away, but negatives are going to pull positive charges toward them. And
Yeah, I meant to say whatever opposite the positive one was.
Yeah.
You said the same thing.
so the arrows just reverse directions. And just because I can, and I don't want you to think it always has to be the same, I'm going to just use 3 arrows this time. So if I were putting this on that same drawing on the previous page, I would use 4 because this negative E is just as charged in a negative fashion as the positive E is in a positive fashion. So if they were on the same diagram, they should have the same number of arrows going into them. But I just wanted to do 3 because that's going to allow me to ask you, how many should we do for negative 2E? 6, exactly. So in this case, I'm going to draw my 3 and then I'm going to add 3 more. So what we've got is a couple of maps, or one map up here, where if we thought about if I put a little positive there, this would tell me which way it's going to go. It's going to be pushed toward this charge right here. It's going to go up and to the left. But I can also figure out how hard it's going to be pushed. If I look at the distance between these field lines, it's not going to be a very big force. If I put a positive charge here, the distance between the field lines is smaller, so it's going to be a stronger force. And if I put it over here, this is going to be a really weak force because these are really far apart. Okay, now it gets a little more interesting. 2 negative point charges in close proximity and 2 positive point charges in close proximity. So I was saying earlier, these, I've got them on the same map. I'm obeying the same rules, that this is 3, and since this is twice as strong, this should have 6. But these aren't really interacting. Now we've got a couple of positive charges that are. So I've got positive charge and a positive charge. And the so-called test charge, this is just a theoretical charge that we just imagine putting in between these that's small enough that it's not actually going to change the electric field. It's not significant. It's just going to get pushed around. So think about what the field lines would look like, and just in your mind place this little positive charge here and here and here and here and all around these, and think about which way it would be pushed at each of those places, and see if you can come up with a kind of a sketch of what this would look like. If you do sketch it, don't sketch it in pen and sketch it lightly so you can change it. But I think it's interesting to think about. I'm going to come around and look and see how people in here are doing, just to see what you've got, because I'm curious. But it's okay if you don't do it right. But it is doable. It is the kind of thing you can figure out the right answer, I think. It's good so far, 100% correct at this point. Yeah, you just draw lines. Good. So there's one part of this that's just kind of a slam dunk that can get you started. And I'll actually go ahead and do what I've seen a couple people doing already. And that is this and this. And we know the field lines look like that because if you imagine putting a little positive right here, it's going to be pushed directly to the right by this charge, and it's going to be pushed directly to the right by that charge. So it's just going to move to the right. And the same thing would happen if you put it over here. Both of these charges are going to push it directly to the left. So that's good. Now see if you can add some more to it. All right, it looks like people are getting kind of stuck. I haven't seen the people at home. Does anybody, like, with your hands, can you show me? Anybody want to? Or you can show me your paper? No? Okay. Well, here, I'll help you think through it. So let's just imagine that we put a little tiny positive charge right there. Which way would it get pushed? What's that? Up. Yeah, so this charge right here would push it this way. And this charge right here would push it that way. And if you add this vector and this vector together, head to tail, you get one that's straight up. So if I were to draw the field line right here in the middle, I would draw it straight up. Now, if I imagine putting it right here, which way would it be pushed there? Generally up or generally down? So these two positive charges are down below it, and they're going to push it away. So they're generally going to move it up. Would it go more leftward or more rightward? Which one's going to push it harder, the close one or the far one? The close one. So if they both push it away, like this one pushes it away this hard, and this one pushes it away that hard, which way is it going to go? It's going to go up and to the left. If I add these two vectors together, I get something like this. So it's going to end up looking something like this. And how many field lines and exactly how you want to do it is up to you. So it's like what I drew on the previous page, except the field lines from the two positive points curve away from one another. If I put a positive charge right here, direct, in between these two charges, where would it go?
Just stay in the middle between them?
It would start out going to the right, though, right? Yeah, so it would just kind of go, if I could perfectly balance it right, it would just go boing, 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 back and forth. But that would be really hard to get it to balance there. If I had it just a little bit higher than that, then it would go like this, and it would eventually get pushed straight up. So this is the general general pattern. So those are two positive points in close proximity. Now if we did two negative points, what do you think? Would it look just like this except with the arrows different, or would we actually be drawing different curves? What? Different. So how would the curves be different, do you think?
I don't know, I just feel like it'd be different if the field is positive.
But it's possible that that I could draw the same curves but just switch the arrowheads and put them at the other end. So let's think about it. What's the easiest place to figure out? Like there, again, on this one, the easiest places were right there. Can you tell me what would happen to a positive charge that's right here? Yeah, it would be sucked right into this. And that's because this one is going to pull it this way, and that one's also going to pull it that way, so definitely the field line is like this. And over here, for the same reason, it's definitely like that. So far, we've got just the reverse of this. What if I put a positive charge here? Which way would it be pulled?
Toward the negative charge?
Which one?
The one closer to
the
it?
closer one, yeah. So there would be a really strong pull that way and a weak pull this way. And if you add those two vectors, you get sort of in between. So it does turn out, if you check all these different points, kind of like we did before, that it's just going to end up being essentially the opposite of what we just drew. It's the same kind of, everything's got the same curve to it, but the arrowheads are on the other end. Like that. And if you had something that was right here, right up in between, halfway between these two, exactly halfway, what would happen to this? Positive charge. It would go down, and would it just stop when it got there? Yeah, this would be like jumping through the center of the Earth if the Earth weren't rotating. It would just go back and forth and back and forth. And if there's friction, eventually it would stop right here. But if there were no energy loss, it would just keep oscillating back and forth. But if it got off to one side, it would go into that or go into this. Last one. So we've done sort of separate positives on the other side of the page with different charges, and then we've got these two like charges close to one another and like charges close to one another. So now we're going to do a positive charge and a negative charge interacting with one another. And I think it is worthwhile to try it yourself before I go over the answers. So see what you can come up with. This will not just be exactly like one of the other ones we just did, but with the arrows reversed, because we've already exhausted all the ways you could point the arrows. So the mental challenge is just to place a hypothetical positive charge all around here, and then use arrows to show which way it's going to be pushed. And I'm trying carefully to not say use arrows to show the path that it'll follow. There's a difference between the way these things will get pushed and the path that they'll follow, because they don't always stay on the path. Oh wait, well, no. That's the one. Yeah.
Oh,
Because
that would attract you as negative.
Yeah, it looks like it's going well so far. Yeah, that's good. Good. Correct so far. Nice. Excellent. I don't know what's going on here. I'm going to, just for the sake of the other class, say that I must be teaching it better this block, but you're doing way better than they did. So nice job. I think I'm going to start in. Most people are on the right track in this. So if you put a positive charge anywhere between these things, it's just going to definitely go straight like this. So right in between the field lines, go straight from positive to negative. And if you had a positive charge over here to the left, now two things are happening. It's being pushed away by the positive, but it's being attracted by the negative. But which one's going to have the stronger effect? The positive. So over here it's going to go like this. And same kind of thing over here. If you put a positive charge here, it's going to be more attracted by that close negative than repulsed by or repelled by the. Because repulsed is when you find something disgusting, right? So it's not a synonym of repelled. But you can be repelled by something disgusting also. All right, just checking. So this would be that. And it's good so far because remember, field lines always leave from positive charges and they always are drawn toward negative charges. All right, so now what about right here? Which way would this, if it were right in between these and up above, which way would it be pushed? This is a tricky question. Which way is it pushed by the positive charge? Up and to the right. And which way is it pushed or pulled by the negative charge? Down and to the right. And if you add these two vectors together, what do you get? You get up and to the, so if I put them together, I could put them together head to tail like that, and then I just get straight right. So at this point, right in the middle, it would be straight to the right. But if I go off to the right a little bit, and let's just talk about here, which way is it going to be pushed at that point? Down and to the right, because this is now pushing it up and to the right more weakly, and this is pushing it or pulling it down into the right more strongly. So if I add these two together, I get something like that. So generally in this area, what am I going to see? I know somebody had it right. Everybody wants to tell me? Can you describe what I would draw right in here? Anybody from home know? I want to draw a nice field line in this area. What should it do?
You could draw like a curvy line that eventually goes down and to the right into the negative charge.
Yeah, where does it start?
Or just a straight line.
So I like this. Where does it start from? The positive. So it's like that. And then symmetrically, there's going to be another one like this. So this continues. It depends on how many field lines you want to put in here. I'll do quite a few. Just, I don't know. I don't really know why I'm doing quite a few, but these, they're going to kind of do this and that, and at some point these may go out of the usable part of my paper. And I don't know that I've spread them out evenly like I should. No. I could add more in here. I feel like I made them a little too tight over here. It looks like this side of the positive thing has got closer proximity, so there's stronger charge here than there is over there. So it's not a perfect diagram, but that's generally what it looks like. So that's it for how to draw field lines. And now, people at home, I'm just about to cut you loose, but let me really quickly go over what's on the homework just one more time. And I know I did this at the beginning of the class, so I wouldn't forget. But so it's the practice, which is on this page, and I think if I look on my website, I put a note on there to, doesn't say anything about it here, but I believe if you go to Google Classroom, it says to not do number 2. So you can do number 2 if you really want to, but I would skip it. So number 1, A and B, these are just sketching, and so this is a charge with positive Q for the charge, and this is negative 3Q for the charge. So make sure that compared to one another, they differ in the way they're supposed to differ. And then number 2, just skip that one. Number 3 is kind of a, you just have to rank these. You can read that later. 4 is new stuff, like what you know, you're going to be using the information I just showed you. 5 and 6, these are just more practice with the electric field equations. So don't feel like you have to do anything with field lines with this. It's just more equation practice. All the answers are there if you need them. And the solutions and even a video is in Google Classroom. Then the other thing, the electric field hockey. Remember, there's no handout in the packet, so you'll need to just look at the questions here and then go to electric field hockey.